Points in triangles. Let's start with the warm-up. We're going to draw a right triangle, equilateral triangle, isosceles triangle, acute triangle, obtuse triangle, and a scalene triangle. So let's start with that first one, a right triangle. Right triangle means that one of the angles is 90 degrees, so two of those sides are perpendicular to each other. There's an example of a right triangle. The next one, equilateral triangle. Equilateral means that all three sides have to be congruent. So there's an equilateral triangle. An isosceles triangle, isosceles just means that at least two sides have to be congruent. So there's an example of an isosceles triangle. Number 2 is also an example of an isosceles triangle. Isosceles just means at least two sides congruent. So three sides can be congruent. The equilateral is just a little bit more specific. It's saying that all three are congruent. Isosceles is at least two are congruent. Next one we're going to do is an acute triangle. Acute means that all three angles are less than 90 degrees. There's an example of an acute triangle. An obtuse triangle. Obtuse triangle means that at least one of those angles is obtuse, or one of those angles is more than 90 degrees. So there's an example of an obtuse triangle. And our last one, scalene. Scalene is just saying that none of the sides are congruent. So there's an example of a scalene triangle. The objectives for this lesson are to discover points of concurrency in triangles and to draw the inscribed and circumscribed circles of triangles. So we're going to start with an activity. Take a piece of paper and we're going to draw or fold a triangle. So I recommend folding makes it easier when we go through and do the perpendicular bisectors and angle bisectors. If you're going to just go ahead and draw it on there, draw it with dark marker or light colored paper so that you can see we're going to end up folding and you want to be able to see those lines. All right, so I folded this triangle and then I went ahead and I outlined the sides of my triangle so that you could see I've got a triangle. To construct the perpendicular bisector, what we're going to do is just fold the paper so that these two vertices touch each other, and that when you fold it, you want the line to match up on itself also. So fold the paper, touching those two vertices together, and having this line, or this side, touch this side also. So make sure those match up. And if you do that, it's going to guarantee that it folded in half at a perpendicular, which is what we want, the perpendicular bisector of this side. And you're going to do that 3 times. So then you're going to fold the next one. And you're going to fold it so that these 2 points touch and that the line matches up on itself. And then you're going to do the last one, have these 2 points touch and have the line match up on itself so that when you open it up, you've got a perpendicular line through the midpoint of that side. Now if you do this, what's going to happen is all 3 of those sides, or all 3 of those perpendicular bisectors of those sides, are going to intersect at a point of concurrency, or at a single point. So here I've drawn in my perpendicular bisectors in red so that you can see, rather than just the folds, you can see that they have a point of concurrency, and this point of concurrency happens to be on the outside of my triangle. Now that doesn't always happen. On my next triangle here, I've folded my 3 perpendicular bisectors, and I've circled the point of concurrency, and it happens to be on the inside of my triangle. So the point of concurrency may be on the outside, may be on the inside, but notice that no matter how you draw your triangle, no matter what kind of triangle you have, if you construct the 3 perpendicular bisectors, they will all intersect in one point. Okay? Do the same thing, well, start with another triangle. And we're going to do a similar activity where instead of folding along the line segment to find the perpendicular bisector, we're going to find the angle bisector. And the way we do that is this time fold it so that 2 sides match up through the vertex of the angle that is formed by those 2 sides. So I'm going to go ahead and fold it, making sure those 2 sides match up, and I want it to go through that point. And what will happen then is when I open it up, I'm going to have 2 congruent angles. So this is going to be the angle bisector of this angle. Do that for all 3 of your sides of the triangle. So fold the next one, making sure the sides touch and making sure it goes through the point, that vertex point. And if you do that for all three angles, you're going to notice that they also have a point of concurrency. So notice I have my 3 angle bisectors, and they all intersect in one point, or in a common point of concurrency. For any triangle, you can draw an inscribed circle and a circumscribed circle. Now, an inscribed circle means that it's inside the triangle. So my inscribed circle is that first one. Notice it is inside. The circle is inside the triangle, and the triangle actually, all 3 sides are tangent to that circle, or they touch the circle one time. So each side touches the circle once. Now, circumscribed circles are on the outside of the triangle, and that's my second one here. This time, each vertex is on the circle. So inscribed circle is inside the triangle. Circumscribed circle goes on the outside of the triangle. Inscribed circles touch the sides, each side one time. Circumscribed circle, each vertex is a point on the circle. Go ahead and grab one of the angle bisector and also perpendicular bisectors. And what we're going to do is take a compass. And if you take the compass with your perpendicular bisector, so here I have my 3 perpendicular bisectors. The point of concurrency of those 3 perpendicular bisectors is going to be the center of my circle. And I'm going to open my compass so that it touches one of the vertices. So I've got my compass open. The center of the circle is going to be the point of concurrency of those 3 perpendicular bisectors, and the radius is going to be the length it takes to go from that point of concurrency to a vertex. Now, if you do that and then you pick up your compass and move it over, notice that it's the same distance to all 3 vertices. What that tells me is if I draw the circle in on that triangle, I'm going to end up with a circumscribed circle. So the point of concurrency for the 3 perpendicular bisectors is the center of the circle that circumscribes the triangle. So it's the center of the circumscribed circle. Each of the distances from the point of concurrency to a vertex is congruent, meaning it's the same, it's the radius of my circle. Now grab that angle bisector triangle that we had. This one had all 3 angle bisectors drawn in. And if you make the center of your circle the point of concurrency, and you measure out or open the compass so that it touches the edge of the triangle, and move it over to another edge, and move it over to that third edge, notice that the distance from the point of concurrency of the 3 bisected angles is the same distance. It's the same distance to each of those sides. So the point of concurrency to the side is the same distance on all 3 sides, which means if we draw the triangle in, and go ahead and draw that triangle in, what you're going to see is that circle is inscribed in the triangle. So the point of concurrency for the 3 angle bisectors is the center of the inscribed circle. I can draw that circle in. Center is the point of concurrency of the 3 angle bisectors, and it's an inscribed circle. So the circle is inscribed in that triangle. It's inside that triangle. The intersection of the angle bisectors of a triangle is the center of the blank of the triangle. This point is called the incenter. Okay, so this is the last one we just had up. The intersection of the angle bisectors is the center of the inscribed circle. And what we call this point of concurrency is the incenter. So the incenter is the point of concurrency of the 3 angle bisectors, and it is the center of the inscribed inscribed circle. Inscribed circle, in center. So the in center is the center of the inscribed circle. The intersection of the perpendicular bisectors of the sides of a triangle is the center of the blank circle. This point is called the circumcenter. Okay, so we have my perpendicular bisectors. Got 3 perpendicular bisectors. Draw a circle. That circle circumscribes the triangle. So it's the center of the circumscribed circle of the triangle, and it's called the circumcenter. So your perpendicular bisectors, draw all 3 of them in, the point of concurrency, that's called the circumcenter, and it is the center of the circumscribed circle. Draw a curve that's smaller than a semicircle. How will you find the rest of the circle by connecting 3 points on a curve as a triangle? Okay, sometimes archaeologists will find like a piece of a plate or a piece of a platter and they know it's circular, but they want to know how big the actual item is. So what we can do, we've got a semicircle. Well, a curve that's smaller than a semicircle. Semicircle would be half. So this is part of it. We don't know what half of it is. If it's half, we can very easily double. So that's why we want one that's smaller. How do we find the rest of the circle? By connecting 3 points on the curve as a triangle. So let's see. If I connect 3 points, so I'm just going to pick 3 points, and if we connect those 3 points, how can we find out how big that circle is going to be? Well, that circle is going to be the circumscribed circle. So if we can find the circumcenter of the circle, then we can figure out how big the radius is, and we can find the size of the entire circle. Well, the circumcenter is the point of concurrency of the 3 perpendicular bisectors. So what I need to do is just draw in or find those perpendicular bisectors, and I can find 3 of them, or I can find 2 of them, because if the 2 intersect, it's going to be the same point where the 3 intersect. But if I want to go ahead and find all 3, that's going to give me the center of the circle. And then I can very easily find the radius, because the radius is just the distance from the center to any point on the circle. And that's going to tell me how big the entire circle is. And so what I have is I've drawn some. Here I started out with an arc smaller than a semicircle, so it's smaller than half of the circle. And I folded this paper. I just folded 2 of them to find the point where they intersect. If I fold the 3rd one, it's going to intersect through the same point because they all intersect in one point. And then by opening my compass, making that point the center of the circle, I can extend my compass to the outside of the circle, finding the radius, and then I can draw in the rest of the circle, or I can find the length or the size of the entire circle. Same thing, this time I drew in all 3. Open the compass, you can find the full distance from the center to the radius, which allows you to find the full size of the circle. So using these points on triangles, or special points of triangles, we can find the inscribed circles, and we can find the circumscribed circles.